So the angle is computed in the anti-clockwise direction, but you can see that it's a multivalued function because the angle from here to here is theta, but they're the same as if you compute it as theta plus 2 pi, or if you are computing it from here to here, it is theta minus 2 pi and so on. So it's a multivalued function. That's something you can easily see. Okay. So, and also for z equals 0, it is not defined at all. Now, what we do in the case of argument, we define the principal argument by restricting it to minus pi. This denoted by the capital A argset. Now, then it becomes single valued. Now, we can do it to make it single valued. You can choose any alpha and alpha plus 2 pi and make it single valued. Now, let us consider the function, very important function called log z. So, log z we define as an inverse of the function exponential function. Okay, so now this computant will tell you that this is a natural logarithm. Log z is given by this ln mod z. This is a natural logarithm of mod z, I into arg z. So here again the imaginary part is arg z, which is multivalued. So it will take different values depending on the argument you choose. So log z again is a multivalued function. So this is expected because log z we derive it as an inverse of exponential z. But exponential function is not 1, 1. You can see that whenever you take say for example e raised 2 pi and e raised 4 pi I has the same value 1. So the same thing will happen. So therefore the inverse will not be well defined. So that is the problem here. However, the functions like z square or exponential function, they don't have such problem because z square is this where again argument comes into picture, but the thing is that it will not contribute to the value, so it becomes 1. So z square means this quantity becomes 1, therefore it is single valued. Similarly, exponential is single valued. But once you take a square root function, you have the same issue. So you can see that issue. Now the root for every such functions problems lies in the notion of argument. Also, it is natural that a function that is not 1, 1 need not have a well-defined inverse. Now let us consider the branch. So for example, you consider the function log z. So in that case, here this argument part creates a problem. Then what we do, in the plane we remove a line, say with the argument lying in this alpha and alpha. So we choose only z with argument lying between alpha and alpha plus 2 pi. That means you remove this line. So then this function becomes single valued. So in fact we could prove that we can prove that w equal to log z is analytic in that particular region. Okay, and I think you proved this in the first course. Otherwise we will discuss it again. Now, what do you mean by a branch? This is called a branch, and I mean you removed a line and you obtained a domain where it is analytic, okay, and it is single valued. So this is a definition. A branch of a multivalued function f is a single valued function g that is analytic in a domain, and for each set in the domain, g set should take one of the values of f set. F set is multivalued, but g should take one of the values of f set. But the thing is that we demand that G should be analytic. Otherwise, what happens is that you can construct any branch, I mean, choosing some random values of f set and all. So what we mean by a branch cut, the portion of a line or curve used to make the single valued branch of multivalued function is called a branch cut. For example, in this case, this line is a branch cut. You can remove any line, you will obtain a branch. So any line starting from origin going to infinity is a branch. So any such line is a branch. Any such line is a branch cut, so something which we use to obtain a branch. And a common point in all branch cut are known as the branch point. Here origin is the branch point. Okay. So this is known as the principal branch. I mean, once you choose the principal argument to define log z, then that is called the principal branch of the logarithmic function. Same thing you can do for root set and several other functions. Now let me come to the final topic of elementary Rayman surfaces. In fact, we will not discuss Rayman surface in detail because it includes a lot of technical things which are beyond the scope of this course, like manifold, the notion of manifold, and other things. But let me just tell you what do you mean by Rayman surface by looking at some elementary examples. For example, you consider w equals z raised to n, where n greater than 1. Then what happens? A small portion of the complex plane, I mean this sectorial region, z with the argument lying between k minus 1 2 pi by n and k 2 pi by n, is mapped onto the w plane. So the image will be the whole w plane except the positive real axis. You can simply verify that. Now in this sectorial region is mapped 1 1 and 1 2 2. This c minus the positive real axis via this maps w equal to z raised to n. Now if you look at the inverse of this, what happens is that inverse of this map it has a branch on the w plane except the posterior real axis, and the image will be this sectorial region. Okay. Now what happens is that this can be done for any branch point. So the whole complex plane you can divide into such sectorial region. In this case there will be n such region, because we are taking 1 by nth root, I mean nth power. So what happens is that you take one rotation around the w plane, then you will end up with the one branch here. Then if you go around it again removing the posterior axis, then you will get another branch, and so on. So what happens that once you fill out the whole complex plane here you will get such n sheets here. Okay. So this is something we call as the Rayman surface associated with this function. So I will show you the picture. So this is the picture regarding yeah. So I think you can see this. Yeah. So you look at z raised to 1 by 4. What happens is that you have one sheet, that means that covered one complex plane. Then the edge we attach to the second one, and so on. So here you have 4 sheets. In general, you will have n sheets. So this is the z raised to 1 by third root. So here you have 3 sheets. So what happens? You rotate once, then the edge you patch it with the next sheet, then again so on. So there will be 3 sheets. Okay. So that is the pictorial representation of this. So if you work with w equal to e raised to z, you can see that this infinite strip will be mapped onto one complex plane with again posterior axis removed via e raised to z. So you will have infinitely many strips. So log set or exponent set will have infinitely many sheets, and you have the corresponding Rayman surface. Now I have given the definition technical just for the sake of completion, but you don't have to worry about the definition because it's involved kind of manifold notion and all. You don't have to worry about that. You just need to look at the elementary Rayman surface created using such functions.